Say it is a hard topic to discuss. Okay, it's hard for me to teach. It's hard for you to understand too. Okay, I do not know if there are any other faculty members who think it's a very easy topic. Then, if any faculty member volunteers to help me with this chapter, I would be glad to collaborate with them. Okay, just send me an email. Sir, it is very easy for me and email Jntuk Moocs, then I'll ask you to teach that chapter. Okay. The reason I say that it's a hard to teach and hard to comprehend also is right. If you are a good programmer, you'll appreciate dynamic programming. You have to be really good in programming to appreciate the nuances of dynamic programming. Okay, that is what I feel. Personal opinion versus bottoms up programming. It's also top-down design, not just programming. Top-down design versus bottoms-up design. So if you take a greedy algorithm, that's typically classified as a top-down approach. Okay. Dynamic programming is the opposite of that. It's called bottoms-up approach. Okay. So what is a top-down approach? What is the characteristic of a top-down approach? What did greedy method tell us? You take a problem, you divide it into smaller sub-problems, right? And then you solve the smaller sub-problems and combine those results for the overall solution. That is typical top-down. That is what we do even when we are trying to solve a problem in the industry, right? We say, okay, you have a system to build. The system is made up of subsystems. So we identify the subsystems recursively. Then we implement those subsystems, and all the implementations of various subsystems forms the total system. Typical top-down. Bottom-up programming basically means you are identifying solutions at the leaf level or the lowest level. You're optimizing those solutions and you're combining those solutions together to form the overall solution. So instead of going from the top, you're going from the bottom. Available solutions, you kind of glue them together to form a bigger solution. So that is the essence of dynamic programming. Now we launch into more discussion with lots of examples and enough time for doing interesting exercise in the class as we go along. Okay. Today my class might be short for the simple reason that I'm actually, if you notice, I'm coughing, so I may not last the full 2 hours. If I last 1 hour, I'll be happy. Okay. It does not mean you're getting free time. Okay, you will do some exercises, right? Okay. As I said, I'll try to make it as simple as possible, but it is a complex topic. Simplest example, counting coins. Okay, I'll go slow. Today I'll go slow, and then next class I'll monitor the chat. So we are assuming you have coins with some denomination. Okay. One, I think I had a 5-cent coin, I think, which I removed. Whether you call it cents or paisa, whatever, right? Yeah, we had a 5-cent also, I think. Yeah. Let me go there and we'll check. So the goal is we want to make 31 cents or 31 paisa out of those coins. So what is the minimum number of coins we need to use for a given coin set? That is the problem that we are trying to solve. Okay. So that gives you the greedy method. Okay, greedy method we take 10, 10, 10 and 1, you get 31. Pretty good. So far, so good. See, originally 5 was there. Okay. So if 5 is not there, what is the solution? Is what we are asking. Okay. Different scenarios. Similarly, we are saying if you assume coin denomination is not there, what is the solution? If you add a coin with denomination 21, what is the solution? So different permutations and combinations, right? Under different conditions, starting conditions. So look what happens. The solution greedy method for 63. If we add a denomination 21, then obviously 21, 21, 21 is 63, right? However, in this example, we'll see soon that greedy method is not always optimal. Okay, so we are making a claim that, hey, greedy method would not always work. Just because we saw some examples here that it is working, it's not a universal solution. Okay, why do we say that? So let's assume these are the following denominations. Okay, let me move this so that we can see the. Okay. So 63 cents is our goal. Okay. So 63 cents ante we'll of course use 21, 21, 21. We can solve it, right? The way we solve this is the lowest cent coin that we need is 1 cent because that's atomic. Because without making 1 cent, you cannot count all the numbers. So that's why you need 1 cent. If you don't have 1 cent, let's say you are going to 9. If I have only 5 cent coin, I cannot get to 9 without 5 cents. So you need 1, the lowest unit. Okay, 1 paisa. Okay. Now to make k cents, the algorithm says, if you already have a k cent coin, then that 1 coin is the minimum number of coins. The goal is, remember, minimum number of coins. Okay. Bear with me. You will see the difference soon. Okay. I'm getting some static. Mute yourself, please, whoever joined. Please mute yourself. Find the minimum number of coins needed to make I cents. Okay. I'll show you the example. And then you have to find the minimum number of coins needed to make k minus I cents, right? We already found for I. So we should look for k minus I. Choose the I that minimizes the sum because the total number of coins should always be minimum. That is the algorithm. Okay. And this algorithm is a divide and conquer algorithm in essence, or brute force, whichever way you call it, it doesn't matter. Okay. So you can see that the moment you say for each one, that means there's a recursion there, right? When you're saying find the minimum number of coins you need to make I cents, and then for rest of the coins, again, you do the same thing, right? Anything to do with recursion, from the previous chapter, we have seen that it could be exponential work. That's why I do not know if you remember in one of the slides, I said you can think, meaning design recursively, but implement iteratively. Iteration is faster than recursion. But the beauty of recursion is it makes it easy for you to understand the design. So that's why a lot of designers in the industry, we use recursion to design solutions. When it comes time to implementation, we convert that recursion into iteration. Okay. So if this is the divide and conquer approach, then it shows that it cannot work for solving the 63-cent problem. Okay. So there's another way of solving it. Okay. And follow this carefully line by line. Okay. So we say, okay, we'll use one 1-cent coin plus the best solution for 62 cents. Note the word best. Okay. Then what do we do? Then we take the next denomination because 1, 5, 10 like that we have, right? Then we take one 5-cent coin plus the best solution for 58, right? Because now, because 63 is the goal, right? And he's doing it for all the solutions. You have a 10-cent coin, so you choose 10 and then the best for 53. What did you have after 10? I think 25 or 21. You say one 20-cent coin plus the best solution for 42 cents. So for each denomination, you're seeing what is the best. Okay. Same thing, 125-cent coin plus the best solution for the remaining 38 to add up to 63. So one of these 5 will give you the best solution. Do you guys agree? If you agree, put it in the chat. If you don't agree, say why you don't agree. So how many recursive problems we solved here? We solved only 5. If you apply the divide and conquer approach, you have many more, right? 62 recursive problems. Here, by looking at the problem slightly differently, you only have 5 recursive problems. Okay? But 5 recursions is expensive too. So is there a better way of doing it than this? That's what the dynamic program solution is. The idea is the following, okay? By the way, there is no way you will understand all of it in one shot, okay? It's like, you have to cover a few more slides for you to start appreciating it. Programming says is solve for 1 cent, then 2 cents, then 3 cents, up to the desired amount, okay? And then you save that answer. Once you save that answer, you don't have to redo that. So first time is the tough part. Subsequent times, the answer is already available to you. What is the best approach? It's kind of like Dijkstra's problem, right? You calculate the shortest pairs, right? We did the shortest pairs problem. Once you compute, right, it is there in memory or in some table. Then it becomes easy. So now you can see that for each new amount n, compute all the possible pairs of previous answers which sum to n. Okay. Now you'll slowly begin to understand. So for example, to find a solution for 13 cents, okay? Cents, you replace it with paisa if you want. So you're going to solve for all 1 cent, 2 cent, 3 cent, up to 12 cents. Okay. Next, choose among solution 1 cent plus 12 cents, 2 cents plus 11, like that up to this one. Okay. So one of these things would be the best answer. That is what dynamic programming solution is going to say. Okay. Now, how does it work? Let's see that. Okay. Now we are saying, let's say the coins are 1, 3, and 4. There's only one way to make 1 cent, right? Because you just use the 1 cent coin. To make 2 cents, you have to do 1 and 1. Okay. To make 3 cents, you use 1 coin. To make 4 cents, you use 4 coin. Okay. To make 5 cents, remember you start with the 1 cent and remaining you take the best coin. Right? You see that? Starting from 1 up to the desired solution, you keep seeing what is the best for the remaining part. Okay. See, slight change of thinking. See, this is not your straightforward thinking that we have learned so far. It's almost like a convoluted thinking, okay? 2 cents plus 3 cents, okay? To make 5 cents, right? So it's all of a sudden it's 3 coins. Which one is better to make 5 cents? 1 cent coin and 4 cent coin, right? Let me stop here for a second. Do you understand this particular slide? Different way of thinking. So we should unlearn what we have learned, so to speak. Okay. So now to make 6 cents, what is the best way to make 6 cents? Visually. 3 plus 3, right? With 2 coins, I can make 6 cents. If I do 1 plus 5, it's 3 coins. 2 plus 4, 3 coins, like that. 3 and 3 is the best solution. Okay, like that. Now, how do we? I'm going to skip the Java algorithm for now. Okay. So when you look at the algorithm that you have seen, basically what it says is there are 60 to solve the problem for 62, right? You have a branching factor up to 62 because 1 plus 62. Okay. Lot of exponential time wasted. Okay. You have 5 ways of looking at it. Remember the second slide that I showed you, not literally second, the second approach. We had 5 recursions as opposed to 31 recursions. Slightly better, but it's still recursion. Okay. Why we use dynamic programming is, remember how we said solve for 1 cent plus the best for the other one. In that approach, you can show the algorithm is of the order of n times k. Okay, it's no longer exponential. Okay, this type of approach gives you better performance. Okay, mute yourself, please. Whoever is talking, mute yourself. Okay, divide and conquer splits the problem into separate subproblems. You solve the subproblems and combine the results. The 3 classic cases that we have seen are quick sort, merge sort, and binary search, right? That's what we do, divide. Okay. They are called top-down algorithms. So them to find the solution to larger problems, as I stated in the beginning. It's just summarizing what I said in the beginning. Okay. You can also think of it as a bottoms-up way of doing it. Okay. Let's look at this one here. I thought I'll remove this slide, but I kept it here anyway. Let me get the slide completely up, then we can talk. You all know binomial coefficients, right? From math, x plus y squared is that equation there. The coefficients are 1, 2, and 1. X plus y cube, you see the coefficients are 1, 3, 3, 1. Similarly for x plus y 4, raised to 4, I mean, like that. Okay. And then you generalize it. When you generalize it, you can see the n plus 1 coefficients can be computed for x plus y raised to n. According to the formula, C is what? Combinations, right? Permutations and combinations, remember? So it's actually a combinatrix formula. And the formula is n factorial divided by I factorial star n minus I factorial. We learned that from our intermediate days, right? In where do we learn that? In trigonometry, I think. Trigonometry, geometry నేర్చుకుంటాం. Okay. Now, this is factorial, right? So very, very inefficient because to calculate the factorial in that equation every single time is very repetitive and very expensive. Okay. So how do we solve the factorial problem? Instead of doing recursion, we use dynamic programming. And how does dynamic programming work to solve factorial problem? Remember, we said we start with the lowest unit. Remember the 1 cent, 2 cent, right? So you, for factorial 0, we know it's 1, factorial 1, it's 1, factorial 2 is that, right? So like that, you use the solutions, okay? You use the solutions for each of these numbers like that. And what are you doing basically then? The way it is done is it is only depending on the previous row. That means, let's say if you're doing factorial 6, right? You are not recomputing factorial 5 because factorial 6 is 6 times factorial 5. Voila. So you're always using the results of the previous step. That way your computation time is saved. Okay. By doing that, you are able to solve the binomial coefficients problem easily. Because now it becomes a linear space and quadratic time are needed. Linear space because the table, right? You can see it's a table or an array, multi-dimensional array. And you only require quadratic time as opposed to exponential time. I don't know if you have done Pascal triangle in your programming class. The first C programming class, this is nothing but a Pascal triangle. Faculty members know, I'm sure you already know that. Okay. Again, I'll skip the programming element of it for now. Okay. What is the question then is, right? Yes, dynamic programming is bottoms up. We find solutions to smaller problems. We combine them. All that is good. Why does it work? Why does that approach work? The approach works because it is based on a principle called principle of optimality. Okay. So I'm going to tell you what principle of optimality is. Okay. In the context of dynamic programming. So what does it say here? This next set of slides are one of the most important set of slides in this course. Okay, so pay careful attention. So what principle of optimality says is if it is applicable if the optimal solution always contains optimal solutions to all subproblems. Okay, we'll see an application of that in Dijkstra's shortest path. We don't do proofs in this class, that level of proofs. When you have a shortest path from A to G, okay, that means B, C, D, E, F are there. Any other paths that take between those two, they also are the optimal shortest paths. Okay, that relies on this principle of optimality. Okay, what does it mean? N cents with the fewest number of coins. Okay, so we are saying, hey, if there's an N cent coin, we use that. Or the set of coins making up an optimal solution for N cents can be divided into two non-empty subsets, N1 cents and N2 cents. If you add those two, it will come to N. So both N1 and N2 are also optimal solutions. That is what that principle of optimality says. So if either subset of N1 or N2 can be made with fewer coins, then clearly N cents can be made with fewer coins, and hence solution was not optimal. So he's proving it by contradiction. Okay. Now, when does it hold? Every optimal solution contains optimal solution to all subproblems. Okay, that is number one. Now this thing that I highlighted in red, typically I don't use red as a text, but sometimes I do, very rarely though. Notice what it does not say. Okay. If you have optimal solutions to all subproblems, then you can combine them to get an optimal solution. It does not say that. It's like, in math, we say A implies B. For people who are not that savvy in math, they think that A implies B means B implies A. It never works, right? A boy loves girl and the girl doesn't love boy, talking about nature and vice versa. So that is what this is. The principle of optimality does not say that, hey, if all the subproblems are optimal, then the whole solution is optimal. It's only coming from the other way it is saying. And here is an example for that. If you look at this coin usage, right? What is the optimal solution for 7 cents? Because we have a 5-cent denomination, 1 cent, we say 5, 1, 1. Okay. Optimal solution for 6 cents is 5 cents plus 1 cent. Agree? Right? Because we have those denominations. But can I now say that optimal solution for 13 cents is optimal for 7 cents and optimal for 6 cents? It is not optimal. The reason why it is not optimal, number of coins it has is how many? 5, right? There is a 10-cent coin, right? Right? So you can divide that 13 cent in subsets with optimal solutions. What are the subsets? 11 and 2. Okay. 11 can be 10 plus 1. And 2 can be 1 plus 1. So we have 4 coins. Okay. So if you choose the 13 cent divided into 11 and 2, then that principle of optimality holds when you go that the subdivisions also have the optimal thing. Okay. And the red one does not apply if you look at the above example. Because just because there is an optimal solution for 7 cents and an optimal solution for 6 cents does not mean that by combining those two you can get it. So you cannot assume the other way around is what the principle of optimality says. So the trick is to find those optimal solutions in dynamic programming. Okay. So for 13 cents, the principle of optimality holds. 13 cents with the subsets of 11 and 2 cents. Subsets of 6 and 7, the principle of optimality does not hold. Okay. Questions, comments? Let me pause here. My chat, let me see my chat. Anyone put any questions in chat? More. Here is some examples. What am I trying to show here? I'm trying to calculate the longest simple path in a graph. Okay. Path does not have a cycle, right? So A, B, C, D. Why is that the longest path? Because if you go A, C, D, you get a shorter route. But if you go A, B, C, and D, you get the longest path. Okay. However, the subpath AB is not the longest simple path from A to B. Why is it not the longest simple path from A to B? Because the longest simple path from A to B can be 1 ACB, right? If you go from A to C to B, then you are taking 4 units as opposed to 1 unit. Okay. So I can give you an example like that and say, hey, does the principle of optimality hold for this problem? And justify your answer, you should explain it, all that is contained in this slide. Okay. Programming cannot be used. Okay. So we said that most often what greedy cannot solve, dynamic programming can solve. But there are cases like this where dynamic programming cannot give you an optimal solution. Okay. So why am I saying that? The reason I'm is good, but when you are solving complex business problems, right? You cannot say, oh my God, I'm going to use the dynamic programming to solve this problem because my professor said that. No, I didn't say that. You have to really analyze the problem to see if a greedy would work, or if a dynamic programming would work, or some other methodology, right? There is no, it really depends on the problem that you're trying to solve. And all this class is doing is, it is exposing you to different ways of looking at a problem and trying to solve them. That's all we are doing here. Now, our famous knapsack problem, let's come to that, okay? We talk about a thief. He can carry 25 pounds. He has to choose n items to steal, right? You know that. And each item has weight and value. And we call it 0, 1 because either you take it fully or you don't take it. So what is the goal? The objective is to select or steal the item such way you can maximize the value but cannot exceed 25 pounds. That is the constraint. Okay. Now we have seen that a greedy algorithm does not find an optimal solution for that. May or may not find, okay, depending on the parameters, right? For now 0, 1 knapsack, it has been shown that a dynamic programming works very well. Okay. And I made a note there for students saying it's very similar to the coin problem. A knapsack problem is very similar to the coin problem. And the easiest way for you guys to remember, it's a legitimate question in exam, right? Show an example where a greedy algorithm does not find an optimal solution, but a dynamic programming approach would work well. And always remember to the coin problem and 13 cents problem, right? Then you will be able to answer that question very well. Okay. So coin problem, we have to make exact amount of change, as you know. In 0, 1, we said we cannot exceed the weight limit. Okay. Let's see how it solves. I do not know how it solves. Yeah, I don't have anything more on that, I think. So to kind of conclude that part of the lecture, dynamic programming relies on working from bottom up. And when you're working, you're saving those results and reusing those results. That's what it is. And then we example that you can always remember to give in an exam for these things is factorial problem. If you save your factorials for 1, 2, 3, 4, 5, then when you're computing 6, you don't need to recompute 6 times 5 factorial. You simply have the 5 factorial answer, you use that. Okay. As I said here, it's a very complex and tricky way of doing it. There's no, I would almost say that there's no scientific way to solve it. It's more art than science. Okay, I see lots and lots of examples in the literature which clearly demonstrate dynamic programming is still more art than science. Okay. Where do we use it? We use it for optimization. Okay. And there are lots of algorithms in computer science. If you take my automata theory, we would discuss a lot of those things. Most of these algorithms that are proposed, they actually take exponential time. So you don't want exponential time algorithms in your code. That's where you try to make it into more like like what did you say there? N star K type, right? Which is not an exponential algorithm. Okay. And how do we know what are the class of problems that are suitable for dynamic programming? Only problems that satisfy the principle of optimality. Okay. So when you have a problem, the sub-problems are themselves optimal. Okay. If you go back to the 13-cent coin problem, the sub-problems of 11 and 2 are optimal, but the sub-problems of 6 and 7 are not optimal. Okay. So we don't want exponential time. That's why we always say we prefer dynamic programming. Okay. So some notes I gave here between greedy versus dynamic. So as you can see the second bullet, right? Once you make a choice in greedy, you are not going back. Okay. That's an interesting thing. In backtracking, you are actually going back. When we take the next chapter, you would know that. So we go bottoms up, taking smaller sub-solutions and then trying to look at many possibilities and choices before we arrive at an optimal set. That's what we did, right? When we looked at the 63-cent problem, we said, what is 1 cent plus the best solution for 62? Then we had another one, what is 2 cents best solution for 61? By having those sets ready, you are able to, at runtime, pick the right optimized solution to come up with your overall solution. So as you can see, there is no litmus test by which one can tell if the greedy method will lead to an optimal solution or not. Greedy may or may not. Okay, that's something that you should remember. Okay. Whereas for dynamic programming, we say, hey, as long as the problem satisfies the principle of optimality, we can solve that. Okay. First bullet is pretty straightforward. Both of them split their input into parts to find sub-solutions and synthesize larger solutions. Most of the divide and conquer, you're splitting in the middle, as you know, like when you did the binary search, right? Not always, most of the time. Whereas in dynamic programming, you're splitting at every different point. Okay. And then after all, we try all the split points, it determines which split point is optimal. Again, going back to 13-cent problem, 11 and 2, 7 and 6. It tried for both. It knows 11 and 2 gives you a better solution. So it saves that in the array. So next time you don't have to revisit what is the most optimum. Okay, that's what the third bullet says. This is the most important principle. To reiterate one more time, principle of optimality is if the sub-solutions of the optimal solution of the problem are themselves optimal solutions for their sub-problems. Okay, so that optimality has to trickle down to the sub-problems too. That's what it says. Remember, I told you somewhere along the way, I said the shortest path problem satisfies the principle of optimality. You can actually convince yourself through an example, okay? It's kind of given here, right? Proof. So you're trying to go from A to B, and intermediate nodes are x1, x2, all the way to xn. Okay. So if path from xi to xj, you can prove it by contradiction, right? If you assume that it is not, then that means A to B via xi and xj is no longer the shortest path, right? So this is a classic case of proof by contradiction, where you can say that, hey, the shortest path problem satisfies the principle of optimality. Okay. But on the other hand, mute yourself, please, of optimality, but he just gives you some other additional theoretical proof here. He takes a ring, right? So you have an undirected graph A, B, C, D, E, and you have edges A, B, B, C, C, D, D, E, and E, A, right? That forms a ring, correct? So the longest non-cyclical path from A to D is A, B, C, D. Okay. Now, if you continue further, if you see B to C on that, okay, it's an edge BC, but it's not the longest path from B to C, because you can go from B to C like you can do BADCE is the longest path. Okay, so you can go from B to A. That means you're reversing the course, right? In a ring. Instead of going directly from B to C, you can go from the other way. So that's the longest path, right? So he's able to prove that the principle of optimality does not apply in this case. Okay. So only for the shortest path it applies, whereas for the longest path it does not apply. Okay. And I gave some algorithm here. I'm getting a little bit tired, so we'll stop after this slide, okay? Unless I have. Yeah, I don't have the energy to go further, but we'll try. So these steps are meaningless unless we take some examples, right? So let's try to take an example and then see if we can understand these steps, okay? So it's a very interesting example that I have here. As I recall, this was a very interesting slide. How do you solve the matrix or matrix multiplication problem? Okay. So you have two matrices here, right? So how do you solve that? Okay. You have n matrices A1, A2, AN of dimensions, P1 times P2, P2 times P3, and so on respectively. Okay. So you want to compute the matrix product for all those matrices, right? So the goal is in what order should A1, A2 be multiplied up to AN be multiplied so that it will take the minimum number of computations to derive the product. Does everyone understand this question? Very interesting problem, right? What we do, we start computing from left, right? We take P1, P2, and P2, P3. We can do that. Then the net result of that matrix would be P1 times P3 are the dimensions, correct? And then you multiply the next matrix and so on. Okay, but that's not the optimal way of doing it. Okay. So what I show here is the cost. When you are multiplying, right? So how do you get to that final value? You understand the dimensions, right? If this is 2 by 3 and this is 3 by 2, first matrix is 2 by 3 and second one is 3 by 2. The resulting matrix would be 2 by 2, right? You all know that. That's why you see 2 by 2 matrix on the right. Okay. So we have to figure out how to compute the matrix multiplication cost. That's what this is trying to tell you. The goal is to reduce the number of computations always, right? So here are some approaches. Whether I'm introducing it to you, I want you to ponder, then we'll come back and review in the next class. Okay. So here is the way you do the matrix multiplication, which I am showing you there. Okay. How many computations are there? You calculate. Okay. Then you get 139 and then you get this one. Okay. So I show you how to compute the matrix multiplication cost. Okay. And you can see when you multiply two matrices, theoretically, I'm showing you what the dimensions would be. Okay, and how you get the cost, how do you get the Cij in the resulting context, how do you compute that? Okay, so it shows you how many multiplications and additions are there to compute Cij. Okay, and using our principle of taking the higher order numbers, we take only multiplication rather than addition. Okay, so it shows you how many multiplications theoretically, that's n multiplications, right? Okay, so when you look at AB, P times R times Q, that takes PQR multiplication. So we actually derive that. Sample and see if that property holds true. Okay, it does. Right, so when you know how many multiplications it takes, I'm giving you three matrices with dimensions 3 times 5, 5 times 8, 8 times 2. And then I'm asking you a question, which is better? Whether you multiply A1 and A2 first, followed by A3. Okay. Or if you actually do A2 and A3 first, and then you multiply A1 with that result, right? You can see the number of multiplications in the second approach is 110, where in the first one is 168. Okay. So how am I able to arrive at those things? This is not like a divide and conquer, nothing like that. That's why this is called dynamic programming. You're looking at an optimal, suboptimal, no. The subcomponents of an optimal problem, they themselves should lead you to optimal results. That's when you. So what is the dynamic design approach for a general solution? Is there a general solution for this? I don't remember. Okay, I'll stop here because I'm actually not able to think also right now. Programming. All dynamic programming algorithms, they rely on the concept of principle of optimality. What does optimality tell us? It tells us, hey, for an optimal solution, the sub-problems also are optimal. Okay, going from top level to bottom. Optimal solution, the sub-problems of an optimal solution are themselves optimal. Okay, but we also said that when you are going bottoms up, just because you have A implies B does not mean B implies A. That's what we said. Okay. And problem, we have optimal solution for 7 cents, we have optimal solution for 6 cents. Just because we have it for 7 and 6, if we combine, we get optimal for 13. No, it doesn't work the other way. Okay. If you already have an optimal solution, the sub problems of that optimal solutions are themselves optimal. Only A implies B is what is correct. Okay. The other two big points that we noted there was, we said, hey, if you take a shortest path from source to destination, okay, all the other nodes that say, hey, from going to A to F via B, C, D, E, the path from B to C, C to D, D to E, they are all optimal. If they are not optimal, then your solution would not be optimal. So it contradicts the statement saying this is the shortest path. So there, the optimality works fantastic. In the longest path problem, the optimality does not work. We showed an example like that similarly. Okay. So that is what we covered. And then we just introduced the matrix multiplication to show how dynamic programming really works here, right? One of the interesting problems in matrix multiplication is when you have many tables to multiply, in which order you would multiply those tables. You might think of this as a math problem, but this is really not a math problem. This is actually a join problem in databases. You have not taken a course in databases. In databases, what we do in order to retrieve the data and then display to the user, when you go online, for example, to Amazon or to any travel site like yatra.com to book your things, right? It is bringing out data for you from a database. Okay. They are actually using this optimization problem so that way they can minimize the number of joins that are done, or in which way they do the join, they optimize that so that way the data can be retrieved faster. Okay. The algorithm that they use for the database retrieval are typically the dynamic programming algorithms. Okay. Okay, I'll stop here. Post this slide deck. I want to see how you can, let me see if you can do this exercise or not. Let me check. Give me 1 second, please. I'm checking something.